Thank you for tuning into this first presentation of the 2021 season of the neighborhood lectures that are put on by Carnegie Science's Earth and Planets Laboratory. Tonight's lecture will discuss the topic of active research at our department, the question of what conditions can form a planet that's capable of supporting life. So far, we only know of one such planet, and that's our own. But even as we speak, however, there's a rover wandering around Mars looking for signs of past life on our planetary neighbor. Unless the origin of life is a common event, we have a pretty low probability of finding it elsewhere in our solar system when we only have a handful of likely places to look. What's changed most dramatically in the search for life beyond Earth has been the realization that the majority of stars in the night sky are surrounded by planetary systems, most of which are quite different from our own in terms of planet size and orbital proximity to their host star. You may have heard of the idea of habitable zone, which is a distance from a star where the surface temperature of a planet is likely to be within the range where liquid water can exist, and liquid water is presumed a necessary ingredient for life. Well, because of a quirk in the methods that are used to detect planets around other stars, a majority of exoplanets discovered so far have been around stars that are quite a bit smaller than our sun. The smaller the star, the closer a planet has to be to that star to be within the habitable zone. And as we'll hear in tonight's lecture, being too close to a star carries some significant risks, one example of which, of course, is the well-known fable of Icarus. Tonight's speaker, Dr. Alycia Weinberger, studies the processes that form planets and what influences whether they might end up being capable of supporting the development and sustaining of life. Her work spans huge ranges of time and space. Her observing program includes both the various early stages of planet formation, but also the end of a planet's existence when their orbits eventually cause them to be accreted to their host star. Her observations make use of a wide range of telescopes, such as those at Carnegie's Las Campanas observatories, but also space-based telescopes such as Hubble and the Sophia telescope that's flown in a 747 aircraft. So not satisfied with just looking through telescopes, Alycia also is involved in developing advanced instrumentation for telescopes, as well as carrying out theoretical studies of the light scattering properties of the smallest dust particles that are found in circumstellar disks where planets actually form. Alycia obtained her PhD in physics from Caltech, and following a postdoc in astrobiology at UCLA, she became a Carnegie staff scientist in 2001. Among her many awards, we were particularly pleased that she was selected to be among the first class of fellows that were elected to the American Astronomical Society just last year. At the end of her presentation, Alycia will be happy to address your questions. And so can I encourage you to type your questions into the Q&A box that you can access down on the bottom right of your Zoom screen. So without further ado, I'd like to turn the screen over to Alycia Weinberger for her presentation, Come Not Between the Dragon and His Wrath, A Tale of Small Stars and Their Planets. All yours, Alycia.
Thank you. Thank you very much, Rick. And thank you all for being here tonight. It's my pleasure to tell you about small stars and their planets. Now, in this quote, King Lear is saying that he might be angry at the people around him. And I think you'll see why I think it's appropriate to think of some of these small stars as being quite angry and asking if their planets really want to be too close to them. So let me first start by defining a small star. So this is a scale model of what the sun and its luminosity are represented by the yellow circle for the size of the sun and by the blue star for its luminosity. That's how bright it is or how much power it's putting out. And to scale is a small star. It's redder in color, and I'll come back to that in a minute. And it has a tiny luminosity. So very generally, we think of these small stars as being less than half the mass of the sun, less than half of the radius of the sun. And together they have an extremely low luminosity, just a few or at most 5% of the power output of the sun. And you can see in size, actually, the smallest of the small stars are not much larger than the planet Jupiter. But small stars really are stars. They're producing energy by fusion in their cores. Now, these small stars also look red because they have low temperatures. Our sun is about 6,000 Kelvin, and these stars have surface temperatures of 3,000 or 4,000 Kelvin. And that's why we call them also red dwarfs or M-type stars. And you'll probably hear me use those terms interchangeably tonight. I usually can't quite help myself from saying M-type stars. But we call them red because they really do put out most of their light in the red part of the spectrum. So if you think about the visible light that we can see from blue to red, the peak of the amount of light that these cool stars put out is in the red, compared to our sun, which puts out most of its light in the green, and plenty of light across, of course, the whole visible spectrum. And just to hit home the point about just how faint these stars are, this is a famous plot in astronomy called the Hertzsprung-Russell diagram that shows the brightness of stars, and the sun here is 1, so the sun would fall right here in the middle, as a function of their temperature. And we plot this in a funny way, where lower temperatures or redder colors are to the right. And that M star designation comes from an old-fashioned way of classifying stars before we really knew why they were the way they were. And M stars were these coolest, reddest stars over here, much fainter, less luminous than our sun. So you will hear me say small stars, red dwarf, and M-type stars as I go through this tonight, and I mean the same thing with each of those. But why are we talking about these small stars to begin with? And the reason is shown in this video, which shows you the solar neighborhood. So right now we're zooming out of the solar system past the planets through the Oort cloud of comets. And you'll see pop up on the right a scale that shows you how far we are from the sun. So it's in parsecs, which is a unit of distance that astronomers like, but that's about 3 light years. So as we move away, we first get to the star Alpha Centauri and its system of stars. We'll talk about it later. And then other stars start popping up. And the stars are color-coded here by whether they're red in color, these small stars, or more sun-like, or even hotter than the sun. And you can see that the vast majority of stars that are popping up in this video are in fact these red, small M-dwarf stars. Now we're out to about 10 parsecs, and we know essentially all the stars that are closer to us than 10 parsecs. And so we really have been able to count that 75% of the stars in the solar neighborhood, and we think the solar neighborhood is just typical of our galaxy, are these very small red dwarfs. So we know that these stars are plentiful, but if we want to be able to study planets in detail, it would really be handy if they had planets, because they're the closest stars to the sun on average. Those would be the closest planets and the most amenable to study if in fact they had planets. So how do we find planets around these stars, or any star for that matter? The oldest way is not to look for the planets themselves, but to look for planetary material. And by that, I mean a disk of dust and gas. And that's both the material that planets can form out of, but it's also the leftover material that the comets and the asteroids, like we have in our solar system, but around other stars, that are the remnants of formation and tell us about how that formation happened. And what you're looking at here is a picture of a disk of dust around a star I'll be talking about later. You're looking at it edge on. So imagine a pizza or a disk or this planisphere, which shows the night sky, and you're looking at it from the edge. If you looked at it face on, it would look like a circle. So we can look for that planet-forming material as evidence that there's a planetary system. We could, of course, also look for the planets themselves. My colleague at the Earth and Planets Laboratory, Paul Butler, pioneered this technique of looking at the motion of the star as the planet goes around it and tugs on its star. The star moves back and forth, and you can measure that velocity with what's called the radial velocity method. And a more common technique these days is also to look for the passage of that planet in front of the star, as seen by us on Earth, where it blocks out some of the light of the star and makes the star appear to dim. And both of these planet finding techniques, the radial velocity technique and the transit technique, work better for small, low mass stars, because a planet of any given mass is able to tug on its low mass star more, or it's able to block out the light of its small radius star more. So these two methods could be great for looking at planets around small stars. But let's start by looking for the planet forming material to ask, do a lot of nearby stars have remnant asteroids and comets? And to do this, we take advantage of a serendipitous discovery made in the 1980s. So you may recognize the star Vega. If you're at all an amateur astronomy buff, you know it'll be overhead in our nighttime sky here in Washington, DC in the summertime. And Vega is a very common star for astronomers to look at because it's bright and it's stable. And so we tend to measure every other star compared to the brightness of Vega. So we know very well how bright Vega is at visible wavelengths, where our eyes can see, and even a little bit longer. And this white line is a model of that brightness of Vega extended to longer wavelengths. So in the 1980s, NASA helped launch the infrared astronomical satellite, whose job it was to survey the entire sky, but now at long wavelengths, out here in the infrared. That's where we look at heat. And it was going to look at stars like Vega for calibration purposes, but also the whole sky to see what it could discover. And so one of the first stars it looked at for calibration was in fact Vega. And rather than measuring what it thought it would see, which is this white line, it instead measured these points that are in red here. And as I understand the story, there was a bit of panic on the team that was supposed to calibrate and run the IRAS satellite because they thought, oh no, something is broken. We're leaking extra light at these long wavelengths. We're seeing way too much apparent light, but really, it shouldn't be there because the star should be all the way down here. But they tested, they went to some other stars, they came back to Vega. The other stars looked okay, Vega didn't. And they realized that what they were looking at was actually the discovery of an asteroid system around a nearby star. And so all of that extra infrared, all of that extra heat, it's like holding your hand next to a hot pavement on a warm summer day, was coming off of dust that was encircling the star Vega. Dust like that is produced in our solar system by the collisions of asteroids and the evaporation of comets. So this was a very exciting discovery, and it was quickly followed by the discovery of 3 more and then hundreds more stars that are encircled by these remnant planetary systems. So what about these small stars, though? Vega is actually a star that's more massive and more luminous than the sun. What about these remnant planetary systems around small stars, the common stars? Well, there, IRAS, although it found hundreds of disks, found only one around a nearby M dwarf. So it's true that these stars are faint, as I said, and so it's harder to find dust around them. But it also now, through surveys from IRAS and also through more recent space telescopes, such as the Spitzer Space Telescope and the Herschel Space Telescope, it really is true that dust is less common around these small stars than it is around solar-type stars or more massive stars. This is the 1M star that you're seeing here, showing how it has extra infrared light. And its name is AU microscopii, which I'll call AUMIC for short, and we'll talk a lot about it in a few minutes. So this was a little bit discouraging in terms of whether we expected to see planets around these small stars, because they didn't seem to have the remnant asteroids and comets that we found around more massive stars. But it turns out that these stars are in fact really rich in planetary systems. So this plot is showing you how common planets are around small stars, low mass stars. So on the left here is planet radius, and here is how much energy they're getting from their star. So if they're getting the same amount of energy as the Earth gets, they're at 1, and if they're getting 10 times as much, they're at 10. So they have to be very, very close to their stars, which are only putting out a few percent of the luminosity of the sun, to be getting just as much energy as the Earth is getting. And the white boxes show where the most planets were discovered by the Kepler satellite, which was a NASA mission designed to find planets by the transit method. And then the darker boxes show where there were fewer planets found. So you can see that here at a similar amount of energy, between 1 and 10 times what Earth gets, and a size just a little bit bigger than the Earth, 1 to 2 times the radius of the Earth, Kepler found a lot of planets around small stars. So in fact, if you add them all up and you combine what Kepler discovered with what ground-based radial velocity searches have discovered, there are probably 2 or even 3 stars per small, 2 or 3 planets per small star. So that's amazing. That means that for the 75% of stars in the stellar neighborhood, we can really expect to find a lot of nearby planets. And right now, the Transiting Exoplanet Survey Satellite TESS is looking for those planets. Okay, but because we have a disk in one case, and we have planets in some cases, we can try to think about what happened to the disks in these systems and how these small stars' planetary evolution might be different than the planetary evolution that happened in our own system. So one thing about small stars is they take a long time to grow up. They are angry when they are young. So they are very high in brightness and in luminosity when they're young, and they put a lot of angry light out, ultraviolet, X-rays, etc. So, and while it only takes the sun 50 million years to reach something like adulthood and to become calmer and reach a sort of steady behavior, it takes a small star hundreds of millions of years to do that. And during that time, it can affect its forming planets. So in particular, these young angry stars that I'm thinking of as the dragons tonight produce a lot of ultraviolet and X-ray light. So this is showing how much light is coming out in the ultraviolet. These are short wavelengths. You would get a very bad sunburn from these. It'd be super bad for you. Coming out from stars of different ages. These are small stars of different ages. So this is 40 million years. So just a baby star, really, 650 million years. So really reaching its ultimate luminosity, its steady state. And then finally, a star that's of a similar age to the sun, say 4 or 5 billion years old. And you can see that throughout this time, even actually once it's reached this kind of adolescence of sort of less angry behavior, these small stars put out tremendous amounts of ultraviolet light. So that is one reason why there might not be disks around most of these stars. So if that light is accompanied by energetic particles, a stellar wind, that can help clear this disk of dust produced by asteroids and comets away and make it such that we don't see them. So the fact that we have a lot of planets and not a lot of disks can in part be due to the fact that these young stars are putting out an angry amount of ultraviolet, X-ray, and protons. So we'd like to go back, though, and study the disk to find out what these planetary materials are made of while the disk is still there. This gives us a clue as to what any forming planets in these systems could be made of, and especially we want to look for those compositions that we think are important for the long-term habitability of a planet. So I and a lot of other people have spent a lot of time looking at the disk around this special star, Emit, the one that IRAS found, and asking what it's made out of and how that young angry star is interacting with its planet-forming material. So at the top here, you see an image of the disk that we made with the Hubble Space Telescope. So this is looking at light that's shining on the disk and reflecting back toward our eyes. So it's kind of like you're sitting in a sunny window and you shake a blanket, at least if I shake a blanket in my house, you produce a bunch of dust and lint, and then you can see the sunlight glinting off of that as it comes in. So that's what we're looking at. The light from the central star is reflecting off the disk and then back to the Hubble Space Telescope where we can observe it. And when we do that, we look at very small dust grains, just a few microns in size, smaller than the width of a human hair. We can also use other types of telescopes, and in particular, there's an amazing telescope called the Atacama Large Millimeter Submillimeter Array in the high mountains of Chile, which can look at the large dust grains that are heated and are radiating that heat back in long infrared and submillimeter wavelengths. And that's what you see in this image. The structure of the disk is the same, but you can easily see that its size is about 40 astronomical units. Let me remind everyone now that an astronomical unit is a convenient measure for the sizes of planetary systems. It's the distance from the sun to the Earth. So it's just a convenient yardstick that astronomers use when thinking about the scales of planetary systems, which are otherwise very big if we quote their sizes in kilometers or miles. So you can see the size of this disk is about 40 times the Earth-Sun distance, 40 astronomical units. And that is very similar to the size of our own solar system all the way out to the Kuiper Belt. So these large dust grains are probably produced in the collisions of asteroids and the evaporation of comets. So we can ask, what are those asteroids and comets made out of? And to do this, we've been using the Hubble Space Telescope to look at the light reflected from these small dust grains. So this is what we think one of the dust grains might look like, because it's a real dust grain from a real comet in our solar system that was collected in the stratosphere of the Earth. And you can see it's not a sphere, it's lumpy, it has a bunch of different components, including some empty space and vacuum in there, and it's a couple microns in size. So we measure the light from the AU-MIC disk using the Hubble Space Telescope in different positions along the disk to try to understand whether the dust remains the same and what its scattering properties are. So we measure how much light at each position as a function of wavelength. And these are visible wavelengths. Here I'm quoting them in microns, but 0.6 microns is 6,000 angstroms or 600 nanometers. That's a visible wavelength to the human eye. And you can see in the points in the background here that the disk looks about the same, though not exactly the same, at every distance from the star. So this red line is our model for what is happening in the disk out at this red point, and this purple line is our model for what's happening at the disk closer to the star, or closer to our line of sight to the star in the purple. And we get this color, the fact that the disk appears to be bluer, have more light coming out at blue wavelengths than at red wavelengths, by trying to understand the size and the composition of the dust. And right now, our best fit composition to these spectra shows that they're made of some pretty familiar materials that we find in the planets in the solar system. They're mostly rock, and they have a surprisingly large amount of carbon molecules or something dark. And one thing that happens to surfaces in the solar system when the sun bombards them with ultraviolet and the solar wind, the energetic particles that come from the sun, is that they tend to turn dark. We call that space weathering in the solar system. And so the fact that we find a lot of dark materials in the AU-MIC disk leads us to expect that those materials have been subjected to this angry young star. And these are the materials that are available to go onto planets, if there are any, and I'll show you in a minute that there are, and are left over from the planet building materials. So should be pretty good representations of what is the planets in this system are made out of. Okay, so I hinted that there is in fact a planet, but we'll get to that in just a minute, I promise. I want to just show you one other really neat thing that was discovered by making these ALMA Atacama Large Millimeter Array images of the disk in order to study the disk and planet formation. So this was a study done by Meredith McGregor. When she did this, she was a grad student, but we were happy to get her as a postdoc at Carnegie a couple years later. She's now an assistant professor at the University of Colorado Boulder, and she's my partner in crime in a lot of these dragon studies. So you'll see her name come up a lot in the rest of this talk. So what Meredith did is she noticed that, yes, she detected the disk, same one that we saw on the previous image and in scattered light, but she also detected infrared emission coming from the position of the star. But if you look at the prediction for how much light comes from the star, which is this black line, and you can see it fits the visible data quite well, you really don't expect to see any light at all from the star. Remember, this is a faint red star. It produces hardly any light out at these wavelengths. And nevertheless, this is the amount of light that was measured right at the stellar position. And there's even more, of course, coming from the outer part of the disk out here. So what is this extra light above what is expected from the star? Well, it could be an asteroid belt. That would be very exciting. That would give the structure of this disk a structure like our solar system, where we have a Kuiper belt out in the cold outer reaches and an asteroid belt in the inner part of the solar system. Or it could be that the star is doing something we don't expect, right? That it has considerably more emission than we expected just from the star itself. And so Meredith did a further experiment, and she went back and looked at data from AU-MIC over time to ask if that amount of light coming from the location of the star was changing. So here's the light on the location of the star, and yes, it's changing quite a bit. And so you can see it's coming along here at a very low level, and suddenly it brightens by about a factor of 20. And then over about a minute, it comes back down again and settles down. And so she realized that this was not an asteroid belt. It was actually a stellar flare, but observed at a wavelength where nobody had ever observed a star to flare before, which is at the submillimeter. We're used to looking at the sun and other stars flaring in the optical, the ultraviolet, the X-rays, even the radio, but not this far infrared type of wavelengths. So Eumik is not just a young and angry star for the average amount of ultraviolet and X-rays that it puts out, it's also a flare star. Now, actually, we've known for years and years that it was a flare star in the visible and ultraviolet. Another Carnegie postdoc, Aki Roberge, and I used that a long time ago to show that there was no more gas in the disk that was available for making gas giant planets, even at this young age of the star of about 20 million years. So this star basically has to be done making planets. Well, was it successful making planets? And I hinted at the answer. And of course, you know, it is indeed true that Eumik has planets around it. So what you're seeing in this movie is how much light is coming from Eumik as seen by this TESS satellite, which is looking for transiting exoplanets. And most of the light that TESS sees varying up and down is coming from the fact that there are spots, sunspots or star spots on the star, these dark spots, and there are flares flashing, which are producing these yellow bumps. If you looked incredibly carefully, and I can't find it with my eye, you can also see a little tiny dip that doesn't look like the others. It's right there. If you take out the other effects, you can see this little dip in the amount of light coming from the star, and that's due to a planet that's passing between us and the star. So we call that Eumik B. It was discovered and published in a paper by Plavchen et al. Just last year. It has the radius of about Neptune, so that's about 4 times the Earth radius. It has a mass which could be up to a couple of Neptune masses, and it's in a really tight orbit. It goes around Eumik in only 8.5 days, right? We take 365 days. We're at 1 astronomical unit. It's only at 0.07 astronomical units. And that makes it pretty close to this even low luminosity star. It gets to a temperature probably of close to 600 Kelvin. Now, very excitingly, this group also discovered a possible second planet. So they're not sure yet, it's unconfirmed, but it's a smaller planet, about half the radius of Neptune, and it's orbiting further out. So it takes longer to go around the star. It has an orbital period of 30 days. It's out more at like an asteroid belt in our solar system, like distance from Eumik. And it would have a temperature of about 100 Kelvin. So neither of these planets is in what Rick brought up in his introduction, this temperate zone where we would be really comfortable. Earth has a temperature of about 280 Kelvin. And so one planet is hotter and one planet is colder. You know, you never know, maybe there's room in between for something else. So this brings up a really interesting question about what happens to these planets. I said they're sort of Neptune-sized now, which means they probably have pretty thick atmospheres, perhaps hydrogen and helium atmospheres left over from the primordial material that was in the Eumik disk, but isn't there anymore. And there's a really interesting observation of the planets around that Kepler spacecraft discovered. So this is a plot of planets that Kepler discovered. This is the planet size. So this is 2 times the radius of the Earth. And this is the period. So we just talked about the outer Eumik planet had a period of 30 days. And Kepler found that there seemed to be 2 groups of planets. So if you look in the colors here, they show in darker colors where there are more planets. If you correct for the fact that it's actually easier to see the planets in here. So you can see that the majority of the planets fall into 2 groups. This group are bigger planets that are further away from their stars, have longer orbital periods. And this group of planets are smaller in radius and closer to their stars. And one idea that's been put forth by a number of authors, this is a plot from Owen and Wu from a few years ago, is that these planets start with very thick atmospheres and they never lose them. These planets start with thinner atmospheres, or they get closer to their stars where it's easy for this angry young star to remove the atmosphere, and they lose their atmospheres and become bare rocks and they look smaller. So this behavior of Eumik and the fact that we don't see much disk material, but we do see planets around this very young star, leads us to wonder whether these planets will eventually wind up in this category or in this category. Will they be planets with atmospheres or planets that are bare rock? And the answer to that may be in trying to understand how this angry star produces light and energetic particles over its whole lifetime. So we said atmospheres can be removed, but they don't have to be. And one thing that we want to talk about as we go on tonight is what older planets around older stars look like in comparison to these young planets around a young star. So let's shift to talking about the second planet in my tale tonight, which is the planet around Proxima Cen. Now you saw Alpha Cen pop up at about 4 light years from Earth as we were watching that movie zooming out from the sun to show all the small stars. So it is the nearest stellar system to the sun, and it's actually composed of 3 stars. It's a naked eye system, but sadly not naked eye visible from Washington, D.C. It's in the southern sky. When I go to observe at our observatory in Chile, though, it's easy to see. So looking at the stars in the Alpha Centauri system, there's Alpha Centauri A, which is just a little bit more massive than the sun, a little bit bigger. There's Alpha Centauri B, which is just a little bit smaller than the sun. And there's Proxima Centauri, which is actually quite far away from them. And it's a little tiny, small, red and dwarf star. It's got only about 12% the mass of the sun, only about 15% the size of the sun. This is to scale. And that means that it's putting out only about 2% the total power of the sun, the total luminosity. So it's one of these really small stars that we were talking about at the beginning, but it's of a similar age to the sun. So in a very exciting discovery several years ago, there was a planet found by the radial velocity method around Proxima Centauri. And so it's named Proxima b. And this was made possible by a long history of radial velocity experiments pioneered by Paul Butler at Carnegie and also carried out by one of our former postdocs, Guillaume Anglada Escudé, who was the primary author on this discovery paper of Proxima b. And they found a planet that had a mass not so different, not so much greater than the mass of the Earth. Its minimum possible mass is about 1.2 times the mass of the Earth. And a temperature that's a little colder than the Earth, but not so much colder, 220 Kelvin. Of course, to get to that temperature is very close to its central star. It orbits Proxima with only a period of 11 days. So it's only 5% of the Earth-Sun distance, 0.05 AU. And now there have been a lot of follow-up papers looking at Proxima b and confirming its properties. And very excitingly, there's tentative evidence for 2 more planets around the Proxima system. So remember, this is the closest M star to us. It's the one that we have the best hope of studying in any detail because it's the closest. And it might have as many as 3 planets we've been able to find around it. It's really amazing. So these second and third planets are called Proxima C and D, of course. Now, I should say that planets are named in the order in which they're found, not in their distance from the central star. So C was the first one that someone thought they had found, and it's out here at colder temperatures further from Proxima, and it has a mass of maybe 6 times the mass of the Earth. So it takes 5 years to go around Proxima. The third planet found, so it's called Proxima D because of the order in which it was found, is actually even closer, perhaps, to Proxima than the one that I just introduced you to. So we're all sure that Proxima b is there. We're not so sure yet about Proxima C and Proxima D. And actually, there's a fun set of tweets going on this week with the hashtag Proxima Live, if you look on Twitter, where a number of astronomers are trying to confirm the existence of Proxima d by taking more data and reporting on their results in real time on Twitter. If Proxima d exists, it would be a planet that's similar in temperature to the Earth, which would be quite exciting. But it would go around its central star in only something like 5 days. So these diagrams show the solar system and the Proxima system to scale in terms of distance, but not to scale, obviously, in terms of the size of the sun and the sizes of the individual planets. It's very hard to actually make a scale model of something so big on my PowerPoint screen. I encourage, if you live in the Washington, D.C. area, sometime to walk past the planet markers that are set out starting at the Air and Space Museum and continuing down the National Mall to get a feeling for just how much further Jupiter is from the sun than the Earth. But this is to scale. So we have our closest planet to the sun, of course, is Mercury. And it's 83 times the solar radius. So if you go out 83 times the radius of the sun, you get to Mercury. And that's about 0.4 astronomical units. Proxima b is not so different. It's 75 of the little tiny Proxima stellar radii out to it. So Proxima would look about the same size in the sky to Proxima b as the sun does to Mercury. And Proxima d is stuck in there even closer, where I couldn't even really draw it on my scale model here. And Proxima c, if it's real, is out at about the same distance as Mars, but it's very cold because it's such a low power star. So this is super exciting that we have so many planets around the nearest star to the sun. And we want, that motivates us, I think, to think about what would the planets be like? And would they be anything, or is it possible that they could be anything like the Earth? So a lot of us, as Rick mentioned, at the Earth and Planets Laboratory are thinking about how to assess whether a planet could be habitable. And right now, since the only example of a habitable planet that we have is the Earth, we want to think about whether other planets could sustain Earth-like features. And by that, we mean things like an atmosphere, a thick enough atmosphere to protect us and to help foster life. Also, whether the planet could maintain a long-term stable climate for which it may need things like a magnetic field and plate tectonics and things that depend on the interior composition and structure of the planet. So we generally think about two aspects of planets when we're trying to think about whether they might be habitable. One is their composition and how that affects their long-term evolution. And the other is their stellar environment and how that affects their long-term evolution. So we could go about measuring the composition of a planet in one of two ways. The most obvious way, of course, is to look at the planet itself. Now, planets are tiny, and looking at the surface of Proxima b is not going to be feasible probably in my lifetime. We might be able to look at the atmosphere of a planet, and I'll come back at the end of the talk as to how we might do that, but we haven't been able to do it for Proxima yet, so we don't even know if Proxima b or c or d have atmospheres. But what we can do is, of course, go to look for a disk and see if there are disk-like materials there. Sadly, as you'll see in a moment, we haven't been able to find one yet, although there was one claimed about 4 years ago when a group used the Atacama Large Millimeter Array and found light coming from the location of Proxima Sun. So this might remind you of what I said about Emit a few minutes ago, where there's light coming from the location of the star. But I don't think these people had read Meredith's original paper to know that there was a chance that it was being produced by flares and not by a disk. So they thought, they were very excited. They had found a disk. Now we could study its composition to find out what the planets were made out of. In fact, they also saw these blobs out here and thought, oh, maybe there's a second disk out there. Once they found one, like they were pretty sure there were two. Well, Meredith and I were both pretty suspicious of this because we knew about her result on Emit, that it was a flaring star. And they didn't show any evidence that they had looked to see if it was possible that the light coming from Proxima was time variable. So one of the first things we did when Meredith arrived at EPL, then called DTM, was we looked to see if the light was time variable. So there were 13 observations taken of Proxima Cen in this campaign in 2017. And if you add up the first 12 of them, you see nothing. There's maybe a tiny little blob here, but it's no more significant than some of the ones out here. And actually these ones in dashed lines are negative. So you see some positive things, some negative things, there's nothing there. But when you looked at the 13th observation, boom, there's this huge amount of light coming from Proxima Cen. And so we thought, aha, this is not a disk at all. This is a stellar flare. And in fact, if you really look in detail at how much light comes from Proxima as a function of time, you see that it's really doing nothing. And then all of a sudden the light shoots up, comes back down, and then it shoots up really high, about 1,000 times its normal quiescent level. And all of this happens in the span of a couple of minutes. So unless you looked at the time, if you average a couple of minutes when the star is doing something really exciting with 15 hours where it's not doing anything at all, you might think there's a little puny disk there, but it actually turns out it was a gigantic stellar flare. And this was the artist's conception that we made, trying to imagine what a flare with the same energy of a solar flare, but on a much smaller star would look like. And our artist's conception of the bare rock of Proxima b there in the front. So this was very exciting, and it made us want to know more about flares. So people have been looking at Proxima for flares in visible light for a long time. And there was a lot of data showing what types of flares it put out. And so this is how many flares happen on Proxima, just in white light that you could see with your eye, as a function of the flare energy. And most of its flares you can see are pretty small, but there's one every day. Sometimes more than one every day. And every so often, Proxima puts out a super flare as big as the biggest flares that are observed on the sun. Maybe even 5 of those a year, 1 to 5 of those a year. So this is a very busy star in terms of its flaring in white light. But what we didn't know is how does the energy that's seen in visible wavelengths compared to the energy that's coming out in ultraviolet wavelengths that can actually harm the atmosphere of the planet, or coming out in particles that could actually harm the atmosphere of the planet. And so to try to understand that question, where do these submillimeter flares belong on this plot of total energy, we decided to put together a gigantic campaign with every telescope we could get our hands on. I often say there's never a telescope that I don't like, to try to understand the flares across every wavelength that we could measure. So all the way from the radio to the X-rays. So to do this requires a lot of different facilities because no one telescope measures at every wavelength. We put together the Atacama Large Millimeter Submillimeter Array. Here's a picture of my son and I are standing in front of that array a couple summers ago. The Hubble Space Telescope to look at the ultraviolet, visible with the TESS satellite and this telescope on the ground called Everyscope, the spectrum of the flare with our telescope at Las Campanas Observatory, the DuPont telescope, there I am with it a few years ago, and then X-ray observatories in space and a radio observatory in Australia. So I'm going to tell you a little bit about the results from this campaign to try to understand Proxima's flares across all wavelengths. And I'm going to concentrate on the telescopes on the left-hand side of this plot. I make it sound like, by the way, I don't want to give the impression that this is all too easy. Not only do we have to propose to all of these telescopes, we had to coordinate them. And I didn't know until I started this that there's actually no way to tell the Hubble Space Telescope I only want to look at Proxima when it's nighttime in Chile, so I can be looking at the same time with these other facilities. So actually programming this took understanding how each telescope did its scheduling. And so we had this giant spreadsheet that Meredith put together. And I just want to show this because we often talk about the great successes we have in astronomy, and we kind of hide what's behind the curtain that makes it difficult. You'll notice some things in red on here, like gyroscope issue, failed to acquire guide stars with the Hubble Space Telescope, or antennas iced over with the Atacama Large Millimeter Array. So those are things you have to face in astronomy. We learn to live with them. And luckily there's a lot of green on this plot, which meant that those telescopes were observing successfully. So I'm going to start with a flare on this night of April 30th to May 1st. So here we discovered the brightest flare ever detected from Proxima simultaneously in the submillimeter and at ultraviolet wavelengths. So here again, there's 1,000 times brightening in the submillimeter wavelengths, and there's a 14,000 times brightening as seen in the ultraviolet from the Hubble Space Telescope. Interestingly, right, most flares have been looked at in visible light, and this was a puny little flare in visible wavelengths. It was in the bottom quartile of that plot that I showed you before. It was interesting. It lit up, seen both from the TESS observatory and from our ground-based telescope, but it was really nothing very special. So when we think about the amount of energy coming out of a flare and what damage that could do to a disk or planet, we really should be more concerned about what's happening at the high energy wavelengths. And at those wavelengths, it was very bright. And it turns out that the submillimeter traces that very well, which is super useful to know because it means that if you have one or the other, you can tell that they would both be bright. So this was an incredibly fast flare at these wavelengths. So you can see here that the top here, these are in seconds. So it brightens over just a second or so and then falls back down again. So this is why we needed a lot of campaign time to measure flares. We don't know when they're going to happen, and then they don't last very long when they do. Although the visible light, this is what we measured from the ground, actually lasted for more like an hour. So this flare has a short impulse, it hits its system, and then it has these longer effects that linger. Interestingly, where it lingers the most appeared to be in the radio. So this was another flare the next night, which we also caught with ALMA and with the Hubble Space Telescope and with our ground-based observatories. But here I'm showing you what happened in the visible light, that's the blue here, and in the radio, which are these curves up here. So this was a flare that was very short and impulsive, similar to the one we looked at the night before, but the radio continued to go up and down for hours afterwards. And that is really interesting because it's extremely similar to what happens in the biggest solar flares that produce not just a lot of ultraviolet and radio, but also a lot of energetic particles, primarily in the form of protons. And those energetic particles are what are most dangerous to planetary atmospheres. So this May 1st flare, while it was kind of puny in the visible, it was super bright in the ultraviolet. It had these long-lasting radio effects. And so what actually happens to the planet is probably not told to us by the visible light flare, but by these other wavelengths that we were able to capture in our campaign. So by analogy, what do we think is actually happening in a flare like this? So the best analogy we have, of course, is from the sun because we can study it so much more easily. And these are gorgeous images that are made by satellites that are orbiting. And they, of course, can look unimpeded by the Earth's atmosphere. So these are taken at very short ultraviolet wavelengths. And you see these loops. These are magnetic field lines. And particles from the sun that are ionized by high energy radiation spiral along these field lines. And we think that's what's producing the radio and submillimeter emission that we measure. Now, if the particles just spiral along and come back and hit the sun again, they might produce a big white light flare, but they don't eject a lot of particles into space. But sometimes these magnetic field lines detach, and then you get what's known as a coronal mass ejection. So there'll be a flare and then boom, all those streaks that you're seeing on this image taken by NASA's SOHO satellite are protons, particles hitting its camera and leaving a streak in the detector. So we would call these cosmic rays if we observe them on Earth. But this is what happens when the sun ejects a huge number of particles, and they happen to be aimed right at the spacecraft and right at the Earth. So some of you may remember this type of geomagnetic storm activity happening in late 2003. They were called the Halloween storms from the sun. The most obvious and beautiful effect on Earth are the aurorae that are created when these particles hit the atmosphere of the Earth and light up the atoms in our atmosphere. So the green and the red are from oxygen atoms that are being excited by being hit by these particles from the sun. But there are a lot of not so great effects on Earth from solar storms. They can knock out grids. They can cause the communication from airplanes to be very difficult. So airplanes have to not navigate in places where they can only use high frequency communication. The radiation effects can be dangerous to astronauts in space. And you can imagine that if the atmosphere of the Earth wasn't protected by our magnetic field, which tends to deflect a lot of these particles or have them primarily hit at the poles, that these would, and if we were constantly bombarded by these, it could really change our atmosphere a lot. And calculations show that bombarding an atmosphere like Earth with these high energy particles causes a depletion in the ozone layer. So you probably know about the fact that depletion of the ozone layer is bad. We did some of it ourselves with chlorofluorocarbons, and we're still recovering from that on Earth. But the sun does that as well. So if you have a very big flare, like the biggest flares that the sun produces or that Proxima produces, you can wipe out 40% of the ozone where those particles are hitting the atmosphere. Or sorry, where the ultraviolet is hitting the atmosphere. And then if you have particles that follow, you can actually wipe out all the ozone in the atmosphere of a planet like Proxima b. And without the ozone, of course, then the ultraviolet reaches the surface, which may or may not be good for life. The other thing that flares can do, besides is they can remove the atmosphere entirely. So they cause the atoms in the atmosphere to just escape over time. And that means that's what I was talking about earlier, where you could go from having a thin atmosphere to having just a bare rock due to the impinging ultraviolet and particles from flares. Now, interestingly, flares also change the chemistry of an atmosphere. And so when we are able to go and look for whether these small planets around small stars actually do have atmospheres, it changes our ideas of what compounds to look for, what molecules to look for, because the chemistry changes when they're hit. So for example, the expectation in a recent paper is that you build up a lot of nitrous oxides. So instead of having water and ozone and molecular nitrogen like we have in the Earth's atmosphere, you wind up building a lot of nitrous oxide. And so when we design our experiments to go and look at other planets' atmospheres, we want to make sure that we're capable of detecting the things that we think would be produced as a result of the dragon firing its breath at these young planets or old planets. So where do we go from here? We really want to search for atmospheres on planets around small stars. We want to know, did these angry young stars remove all the atmospheres or did they survive? Is it possible that these planets could still have habitable conditions? So we're thinking about how to do that experiment of searching for atmospheres with a number of coming space telescopes. The first is the James Webb Space Telescope, which will launch hopefully in the fall of this year. It turns out it'll be very hard to detect the atmospheres of planets with James Webb, but maybe just possible for the very best cases. So if there's no atmosphere, you'd expect this transit depth, which is how the planet looks as it goes in front of the star as a function of wavelength, just to be flat. It would just be a bare rock. It would block the same amount of light at every wavelength. But if the planet has features like water in its atmosphere or carbon dioxide or nitrous oxide, then you'd expect its spectrum, if it's like Earth, to look something like this blue curve. And you can see that maybe with JWST, it would be able to tell the difference that this part of the spectrum is high and this part of the spectrum is low, and it's not a flat line for the very best cases. Probably we'll be able to do a very good job looking at the atmospheres of planets a few times the size of Earth, but we might not be able to do that well for ones that are actually Earth-sized. The next big step will come with the next generation of extremely large ground-based telescopes. So this is the Giant Magellan Telescope. It's a telescope that Carnegie is partnering in building at our observatory at Las Campanas Observatory in Chile. We hope that it is up and running in the early 2030s. And there we actually have such a big telescope, 25 meters in diameter, about 4 times as large as anything that currently exists on Earth, that we think will actually be able to image planets. We'll be able to block out the light of the central star, and the light of planets like Proxima Centauri will peak up. And then we'll be able to break the star into its component colors and find out what it's doing, whether it's flaring. And we'll be able to take the star and look at whether it has, for example, molecular oxygen. This is a spectrum of molecular oxygen. And our hope is to be able to do that for planets like Proxima b and ask if they have oxygen in their atmospheres. And then even beyond that, later in the 2030s, the hope is that NASA will launch a very big space telescope. This one is called LUVOIR. It's a 15-meter space telescope that would actually be able to look at the atmosphere of an Earth-like planet in some detail. So this is a model of what a planet might look like in around a small red star called TRAPPIST-1. And you can see that it has features in the spectrum due to things that we know and love on Earth, like water, oxygen, ozone, carbon dioxide. And these points show what we would be able to do with the James Webb Space Telescope. That's what I showed you before. It's really hard. But these black points show you what we'd be able to do with a really big space telescope, where we'd really be able to understand the composition of an exoplanet atmosphere around an Earth-like star. So I hope I've showed you a little bit about how we're testing the limits of the dragon's wrath. We don't know yet whether the dragon has totally incinerated these planets or whether they've managed to survive the angry young and ongoing outbursts of their stars to reach mature ages with the conditions that allow habitability. But these kinds of multi-wavelength studies that I showed you are the clues that we need to understanding what the stellar environment is and what it does to the planets that are around our nearest neighbors, like Proxima Centauri. So I'd like to stop and thank Carnegie and Meredith McGregor and Evgenia Shkolnik, both former postdocs in our department, and all the other members of this Proxima Flare project who have worked really hard to make it work and bring you a lot of the data that I have showed tonight. And now I'm happy to take your questions.
Thanks so much, Alycia. It's so exciting to see how much information we have now for exoplanets when you consider that we didn't even know that exoplanets existed just a bit over 20 years ago. So this field is just moving forward at an incredible pace. We do have quite a few questions here. Let's start with one. It says, why do these low mass stars put out lots of UV light when they're relatively cool?
Right. Well, that's the interesting question that that we didn't really know the answer to when we were just looking at them in the visible. So we think that most of the ultraviolet comes from a combination of flares and the very outer layers of the star, which can be much hotter than what we call the photosphere, which is what I normally am quoting to you as the temperature of the star. So the sun has a corona, which is millions of degrees, and it has these flares. And most of the ultraviolet and X-rays is coming out during the flares, and not just the big ones, but all the little ones that are happening all the time. And we think that those flares are created when the magnetic field of the star breaks and reconnects. And one open question, which I didn't talk about, is whether the magnetic field of small stars like Proxima really looks like the magnetic field of the sun. It probably has a very different geometry. Some evidence shows that it's both larger, the magnetic field is higher, but also that it might be more complicated in shape. It's possible that that shape directs more of those energetic particles back to the star without letting them escape to hit the planet.
There's a bunch of questions about whether the other stars in the Alpha Centauri group have planets around them.
Right, so that's a great question. We would love to know that. So a few years ago, it was claimed that there was a planet around Alpha Centauri Alpha Centauri B. And it seems like in further analysis of the data and more data taken that that planet is not there, and that a constantly confounding signal that makes it difficult to find planets is what the star is doing. And probably that original detection, which turned out to be false, of a planet around Alpha Centauri B was because of what the star was doing and its spots and its rotation. So as of now, we don't know about any planets around the other stars. Those two stars are harder to find planets around because they're solar type in mass and size. And so those techniques that I talked to you about don't work as well with them, but people are still trying really hard. And we're also trying them from the ground, because they're so close, trying to separate, concentrate the light of the star and block it out and look around them with our telescopes to see if we find something. So nothing yet, but we will keep looking.
So here's one that I hope has an easy answer, but I'm curious what the answer is as well. So is there a Proxima A, or do astronomers start with B for some reason?
We start with B for some reason. So, you know, these choices weren't made extraordinarily collectively or well in the early days of naming planets. But yes, we start with uppercase letters to denote stars. So Proxima is actually Alpha Centauri C, capital C. So there's Alpha Centauri capital A, that's the brightest star, Alpha Centauri capital B, the second brightest star, and Alpha Centauri capital C. Then we use lowercase letters to denote the planets. And we don't start with A because I guess that was considered confusing with the star. So we start with B as the first one discovered, and then C and D, but all lowercase.
Okay. Here's a good one. Why is the duration of solar flare different in different wavelengths?
Right, that's an interesting question. It probably has to do with the physics of what's actually happening in the flare. So some of the light, and we think this is true for example, the submillimeter light and the ultraviolet, are produced by electrons spiraling along those magnetic field lines. And that is what starts the flare. You accelerate those electrons, they spiral, they produce light. Then those electrons smack into the atmosphere of the star, and that produces the visible light that you see in the flare. And that can go on for much longer as you rain these electrons down on the star. Then you also emit particles and a shock wave, which hits gas in the outer layers of the star, and that produces this radio emission that goes on for a long time. So each of those wavelengths that we look at tells you not just about when things were happening, but where they were happening and in which part of the magnetic field of the star they were happening. And it's one of the reasons that it's so important to look across so many wavelengths to get a full picture of the physics of how this works. That's a great question.
There's several questions that ask about if these planets are so close into their stars, are they tidally locked? And what would be the consequences of one face of the planet always facing the star?
Right. So tidally locked, for those who may not know, means what it means for the moon and the Earth. So we always see one side of the moon. It's tidally locked to us. So that tidal locking happens over time due to the gravity, the effect of the gravity of the Earth on the moon. And it causes the moon to face, as it goes around the sun, only one side, as it goes around the Earth, only one side toward the Earth. So similarly, these very close-in planets probably tidally lock to their stars. What we don't know is if they tidally lock like the moon locks, where we only see one face, or they tidally lock like Mercury is tidally locked to the sun, but it spins still, so that it spins 3 times for every 2 times it goes around the star. So you can have tidal locking, but you can, where you only see one face, but you can also have tidal locking where you're still spinning, but at a different rate than you might have been if you didn't have the effect of gravity. So what is the effect on the planet? Well, certainly if it has one side always facing the star, that side is much hotter than the other side. If there's an atmosphere, the atmosphere can help redistribute heat from one side to the other. But if there's no atmosphere, then you have a bare rock, you're definitely going to be hotter on one side. One side would also, of course, be more smacked by the energetic particles and ultraviolet. But again, if there's an atmosphere, it circulates around and it carries with it the signature of what happened on one side to what happened on the other side with winds. And so those models I showed you of the changing atmospheric chemistry due to flares actually took into consideration the 3-dimensional motion of an atmosphere around a planet that would basically distribute the effects from one side to the other side. But it does mean that if, as you look at one part of the planet or another, you might be able to see a time delay in what's happening on the planet due to which side got smacked by its star first.
Alycia, there's a couple of questions about the planets themselves and the role of their formation. So one is going all the way back to disk is, what is the elemental composition of dust particles in the disk?
Right. So as far as we can tell, most of the dust is silicon and oxygen, which is true for dust in other planetary systems and true for the dust in our own planetary system. That's rock, what makes up rock. And then in addition, there's carbon and metals like iron and sulfur. And if the dust is cold enough, it can have water ice. Although when the ultraviolet of a flare hits water ice, it can be photoevaporated quite quickly, and then it leaves just vacuum in its place.
So that's actually a good lead into the next question about it is, what are the ways that exoplanets get their atmospheres in the first place?
Right. So, we don't entirely know, but there are 2 main ways that a planet can get its atmosphere. it forms in a disk, which initially starts out with a lot of gas, 100 times more gas by mass than dust. And so some of that gas can basically just by gravity get pulled into the planet, if the planet's big enough. Some of that gas can also dissolve in the hot magma on the planet when the planet is just forming. And so then when the magma eventually cools, as the planet evolves over time, that gas has been trapped. So one idea for planets that are in these hostile environments with angry young stars is that maybe the star's light was in particles were able to remove that first atmosphere that came in, the hydrogen and helium primarily, that was left over from the original disk that the planet captured. But that over time, the water and other gases that dissolved in the planet originally could come out slowly and make a secondary atmosphere. And indeed, that appears to have happened on Earth, that we also had a magma planet early in our evolution. And we also have had an atmosphere generated by that magma exsolving its gases. So we don't know yet for these small planets whether they even have atmospheres. And it'll be a really interesting question eventually, hopefully, to find out whether they're primarily hydrogen and helium, like they came from the original disk, or they're primarily heavier things that probably dissolved in the magma and came out later.
So here's let's end with a few questions about going forward on this. And there's actually a couple of really interesting questions. Is there a role for amateur astronomers in monitoring nearby red dwarfs for flares?
So that is a good question. There is a very active group of amateurs who do both things. They monitor for flares. And yes, it is absolutely possible to monitor for flares. And especially if you can monitor in a different wavelength than what other people are doing. So to sort of spread out, one person monitors in blue light and one in green light and one in red light, that can be extremely helpful. And a lot of that is coordinated by a group called the AAVSO, which is the American Association of Variable Star Observers, the executive director of which is actually another former DTM postdoc. And they coordinate observations and also collect the observations that amateurs make of varying stars, variable stars. And actually, some amateurs also observe the transit of planets. So they can observe both the flaring of the star, but also and the rotation periods of stars, but also the planets.
Okay, here's a couple related questions. One is, what's the difference between a red dwarf and a red giant? And then the second part of that is, could there be planets around red giants like Betelgeuse?
Yeah, so red giants are stars that are at the ends of their lifetimes. So they started as stars that are as massive as the sun, and now they are using up their nuclear fuel. They're not able to fuse stably hydrogen into helium in their cores anymore. And they start puffing up their outer atmospheres. And as the outer atmospheres slowly expand, they cool. And so they are also red. They're also the same temperature as the red dwarfs that I was talking about. But they started as more massive stars, and they're at the ends of their lifetimes, and they're not very stable. So they can collapse, they can expand, they're blowing off their outer atmospheres. The sun, when it reaches the red giant stage, will expand so much that it'll certainly eat Venus and possibly Earth. So on the existential threats to worry about in 10 billion years, you can worry about that one. But yes, there could be planets around them for sure. Some of them will be eaten. Some of them will remain and will eventually maybe fall back into the white dwarf that red giant eventually becomes. As Rick mentioned at the beginning, that's another topic that I'm interested in. And there have been attempts to find planets around red giants. I don't think there are some around stars that are just starting to become red giants, but Betelgeuse, it's really hard. Most of what we see around Betelgeuse is all of the atmosphere of the star that it has lost in this process of being a red giant.
Okay, let's end tonight's questioning with this one. I like this. It's a more of a personal question. It says, you clearly love your work. What experience or factor influenced you to say, this is what I want to study?
Well, I always like to turn that question around and ask, when did you stop wanting to study astronomy? Because almost every kid I've ever met loves astronomy and thinks it's cool. I guess I just never grew up. I always wanted to ask these questions about our place in the galaxy, our place in the universe. Happily, I came from a family that was very supportive of that and encouraged me to keep asking those questions, and even to the impractical level of becoming a PhD scientist and asking them as a career. So I'm very fortunate in that respect. I'm lucky every day to go to work and do something that I really and thoroughly enjoy. And so I would just say, especially if there are any young people out there listening, please just keep asking the questions that you're so good at asking and letting your natural curiosity carry you through the rest of life.
Thanks, Alycia. Before we say our final thanks for Alycia, let me point out a few upcoming events. One is that we are now trying a new thing in our webpage and social media feeds, where we're highlighting one of the areas of research that we do at EPL every month. And this month is Astronomy Month. So the questions that we couldn't answer tonight, please enter into our social media feeds. They should be available on our web pages, and they will be answered by email or by social media feeds back. And then finally, I'd like to point out that there are two upcoming events. One is on a topic quite related to tonight's talk, and that's going to be given by Sarah Seeger, who was a former DTM staff scientist, now at MIT. It's on the Carnegie programs, and it's given March 30th at 5 p.m. The title's Exoplanets in the Search for Habitable Worlds. And then our next upcoming neighborhood lecture from the Earth and Planets Laboratory will be given by another former DTM postdoc, in this case, Graham Pearson, who's now a Canadian Excellence in Research Chair at the University of Alberta. That will be April 29th at the usual 6:30 p.m. time. And his title is Exploring for Diamonds and What They Tell Us About the Earthwork. So instead of looking outwards, we're going to be looking into the Earth's interior in this one. So please, thank you all for attending tonight. Thank you all for your contributions of questions. And please help me thank Alycia for this marvelous presentation. Thank you all.